Hey y'all, welcome back. On tonight's homework, we are practicing for the AP test. Specifically, we're going to be working through some multiple choice questions. Now, on the actual multiple choice section of the AP test, there's a total of 45 questions, but they're split up into two parts. Part A, which is where you do not get a calculator, gives you 60 minutes to work 30 questions. That's 1 hour for 30 questions. And if you work that out, that comes out to 2 minutes per question. Now, that doesn't mean you have to spend exactly 2 minutes on each question. Some you'll be able to work a little faster, some will take a little bit more time. But on average, you should be targeting 2 minutes per question, which is why on this homework, since there are 9 no calculator questions, I'm giving you an 18-minute time limit on here. And I know that as I try to talk about how to work these problems, sometimes it takes a little longer than 2 minutes as I'm trying to explain how you would work these out. I'm going to try to keep my explanations brief, a little bit more brief than usual, to try to stay under that 18-minute time limit. The second part, part B, is only 45 minutes, so a little less time, but there are half as many questions. On the calculator section, they only give you 15 questions, but give you 45 minutes to work them. So that works out to be, you want to target 3 minutes per question. Again, some a little longer, some a little shorter, but on average, you should be spending no more than 3 minutes per question, which is why on this homework, we've got 11 questions on this calculator section. And so you should really limit yourself to 33 minutes if you're really trying to practice and get ready for that test. So let's go back to the beginning. We'll start with the no calculator section. I'm going to try to go through these as quickly as I can, but still hopefully adequately explaining how I'm solving the problem. So let's start with number 1. It says the graph of the function f is shown. As shown below, consists of 2 line segments. If g is the function defined by g of x equals the integral from 0 to x of f of t dt, then what is g of -1? So to solve this, basically all you need to do is substitute in -1 for x, which gives you g of -1 equals 0, the integral from 0 to -1, f of t dt, which is, when you're finding a definite integral, you're finding the area between the curve and the x-axis. And it is a signed area, so the area above the x-axis will be considered positive, the area below will be considered negative. And so since we're looking at the area between -1 and 0, we're looking for this area right here, which is a little triangle. So at the end of the day, we're just going to be finding the area of a triangle, which is 1/2 base times height, where we can see like this side length is 1, this side length over here is 2. But there is one little quirk to this problem, and that is, if you'll notice, these boundaries, these upper and lower limits, are kind of backwards. So if we want to fix those, what we can do is we can negate the overall integral and swap those boundaries out and go from -1 to 0 so that they're in order. And now I can just use my 1/2 base times height formula here. So I'm going to have negative, and that's from switching the signs to make sure that they're in the right order here. 1/2 times the base, which is 1, times the height, which is 2. -1/2 times 1 times 2 is -1. So the answer is B. Number 2 is asking for the limit as x approaches -3 of this rational function. Now there are 2 different ways that we could solve this, 2 different methods. One method that we could use to solve this, to find this limit, is to factor and cancel. In other words, if we factor both the numerator and the denominator and then cancel out the like factor, we can then use direct substitution and find our limit. The second method that we can use is called L'Hopital's rule. Now, be careful using L'Hopital's rule. You don't want to overuse it. L'Hopital's rule only can be used if you get an indeterminate limit when you find the limit of both the numerator and the denominator. And what I mean by that is if I find the limit of the numerator by substituting in -3 on top, I'm going to get 0. But if I do it on the bottom, I'm also going to get 0. So the limit as x approaches -3 of the numerator 0, the denominator 0, and that is what I mean by an indeterminate limit. And so if you get something like that where you have 0 over 0, you can use L'Hopital's rule. So let's go through the factor and cancel technique. The numerator here, so I'll just say the limit as x approaches -3 The numerator is a difference of two squares and can be factored as x plus 3 times x minus 3. The denominator can be factored as x plus 3 times x minus 5. Notice here that we have x plus 3 in both the numerator and the denominator. So because we're within the context of limits here, it's okay to cancel those out, and we get x minus 3 over x minus 5. And now we can do direct substitution. We could put that negative 3 into x in the numerator to get negative 6, and we could put negative 3 in the denominator to get negative 8. Negative 6 over negative 8 reduces to 3/4, so we can see that our answer is C. Now, L'Hopital's rule, again, can only be used if the limit of the numerator divided by the limit of the denominator is indeterminate, which in this case it would be. And so the way this works is you can find the derivative of both the numerator and the denominator separately and then try direct substitution. So if I find the derivative of the numerator, x squared minus 9, I'm going to get 2x. Well, yeah, just 2x. And the derivative of the denominator would be 2x minus 2. If I substitute in negative 3 at this point on the numerator, I'm going to get negative 6. And on the bottom, I get negative 8, just like I did with the factor and cancel technique. And so either way, I'm going to get 3/4. For number 3, I'm trying to find the integral of this expression. Now, you can find the integrals of each one of these terms separately. Like, in other words, you can find the integral of 5e to the 2x dx and the integral of 1 over x dx and add those together. Now, the integral of 1 over x dx, that's just one that you have to know. That's one that you should know is the natural log of the absolute value of x. So there's not really a whole lot of work to do there. But to get the integral of the other term, the 5e to the 2x, we're going to have to do a little u-substitution. We're going to use 2x as the u. So up to the side here, I'm going to just say let u be 2x. And if that's the case, then du would be 2 dx. Now, I don't have a 2 dx in my expression here. I've got a 5 dx. So I need to divide both sides by 2 and multiply both sides by 5 to get 5/2 du equals 5 dx. And now I have that 5 dx that I have in the original problem, so I can make that substitution. So maybe I'll just do the substitution over here and then kind of go back to the original problem once I figure out what this integral is. So when I make that substitution, I'm going to have the integral of e to the u times 5/2 du, and the integral of e to the u, that's something that you should know, is itself, right? The integral of e to the u is just itself plus c. So this would be e to the u plus c, and of course times 5/2. Now, u in this case was 2x, so I should have 5/2 e to the 2x plus c. And now I'm going to go back and just kind of fill all that in. So the integral of this left term is going to be 5/2 e to the 2x, and then I'll throw in the plus c at the very end, plus the natural log of the absolute value of x plus c. And so we can see our answer is B. For number 4, we are finding the derivative of a given function and then substituting in the number 4. So first, let's find the derivative. And to do that, I think it might be easier if we rewrite f of x as a sum of powers rather than having all those square roots and fractions all over the place. So I'm going to rewrite f of x as x to the 1/2 power plus 3 times x to the negative 1/2 power. So that way I can just apply the power rule to get the derivative. So applying the power rule would give me 1/2 x to the negative 1/2 minus 3/2 times x to the negative 3/2. And evaluating this at x equals 4 is probably going to be a bit easier if we go back and rewrite this as fractions and roots. I think it's easier to do the differentiation if you convert these two powers. But if you're trying to evaluate this, especially without a calculator, I think it'd be easier if we just go back and put the square roots back in. So this would be equal to 1 over 2 times the square root of x minus 3 over 2 times the square root of x cubed. And so if I want f prime of 4, I need to plug in 4 into each of those x's. So 1 over 2 times the square root of 4 minus 3 over 2 times the square root of 4 cubed. Okay, square root of 4 is 2, so this would be 1/4 minus, let's see, square root of 4 is 2, 2 cubed is 8, 8 times 2 is 16, so this would be 3/16. 1/4 is the same thing as 4/16, so 4 minus 3 is 1, so we get 1/16, and our answer is A. For number 5, it says let f be a differentiable function where f of 2 is 3, f prime of 2 is -5, and let g be the function defined by g equals x times f of x. Which of the following is an equation of the line tangent to the graph of g at the point where x equals 2? So we're writing an equation of a line, and to do that we want to write it using point-slope form like we have all year long. So what we need is we need a point and we need a slope on, be careful here, we're looking at function g. So the point should be in the form x, g of x, and the slope will be the derivative of g of x. Specifically, x is 2, so the point would be 2 comma g of 2. Okay, so g of 2 would be 2 times f of 2, and f of 2 was 3. So 2 times 3 would be 6. The slope would be g prime of 2. Okay, so to get that, well, we are going to need to find g prime. So I'm going to kind of go over here and find what g prime is. Now to find g prime, we're going to go back to the function g, which is x times f of x, and we're going to perform the product rule. So the product rule, if you don't recall, is if you have a product of functions and you're trying to find the derivative of them, you're going to differentiate the first times the second plus the first times the derivative of the second. So f prime g plus f g prime. Now I know that I'm using f and g there just sort of generically. These have nothing to do with the g and the f in our problem here. So maybe it'd be better if I use different letters there, but really I'm just trying to remind you of what the rule is. So the derivative of x is just 1. So 1 times f of x plus x times the derivative of f, which is f prime x. And so if I want g prime of 2, and that's in order to get that slope, I'm going to need to calculate that out. It'll be 1 times f of 2 plus 2 times f prime of 2. Okay, so let's see here. F of 2 was given as 3, and f prime of 2 was given as -5. So we have 3 plus 2 times -5. 2 times -5 is -10, plus 3 is -7. So g prime of 2, the slope of our tangent line, is going to be -7. And so now that we have the point and the slope, we're ready to write our equation in point-slope form, which is y minus y1 equals m times x minus x1. Okay, our x1, y1 is 2, 6. So we should have y minus 6 equals the slope, -7 times x minus 2, and we can see that our answer is B. Number 6 says the table above gives values of f, f prime, g, and g prime at selected values of x. If h of x is f of g, then what's h prime of 1? So first, let's find h prime. We're going to have to use the chain rule here because it is a composite function. So h prime should be f prime g times the derivative of the inside, which is g prime. So if I want to evaluate h prime 1, that's going to be f prime of g of 1, which we'll find in the table, times g prime of 1, which we'll also find in the table. So g of 1 is -1. G prime of 1 is 2. So I'll have those two values. We have f prime of -1 times 2. F prime of -1 is also given in the table. It's 5. So this is just going to be 5 times 2, which is 10. Number 7 says the table below gives values of a function, f, and its derivative at selected values of x. If f prime is continuous on the interval -4 to -1, what is the value of the integral between -4 and -1 of f prime? Now, if they ever give you like one point and are looking for another point, And this is not exactly that case, but if you ever get a question like that, and I think we're going to see a few in the coming problems, these are going to be examples of the fundamental theorem of calculus. Okay, so the fundamental theorem of calculus gives you a way to evaluate a definite integral. In this case, we're trying to evaluate the integral from -4 to -1 of f prime x dx. And the fundamental theorem of calculus says you find the antiderivatives of whatever you're trying to integrate, which the antiderivatives of f prime is just f, and then evaluate f, or those antiderivatives, at the limits of the integral. Okay, so f of -1 minus f of -4. So both of these values can be found in the table. F of -1 is -1.5, and f of -4 is 0.75. So we have -1.5 minus 0.75, that's going to be -2.25. Oh, not D. Let's take that back. It's B. Went a little too fast there. I know I'm trying to keep a quick pace here, but it is important that we, just make sure we check our answers here and, answer carefully. 8 says if G is an antiderivative for F and G of 2 is -7, then what's G of 4? Here's an example of what I was really trying to get at earlier. This is another fundamental theorem of calculus problem. So let's set up our integral here from A to B, okay, of f of x dx. Since G is the antiderivative of f, this is just going to be G of B minus G of A. This is what the fundamental theorem of calculus says. So if we're trying to find G of 4, basically what we're going to do is use 4 and 2 as our limits of the integral, our A and our B, and then kind of fill in the numbers as we have them. So the integral from 2 to 4 of f of t dt, I guess, it doesn't really matter x versus t, but I'm looking at the answer choices and they are in terms of t. So so f of t dt equals g of 4 minus g of 2. Now we're trying to solve for g of 4, so we are going to add g of 2 to both sides. So we get g of 4 equals g of 2 plus the integral from 2 to 4 f of t dt. That's as far as you really need to go here. You don't see that exactly in any of the answer choices, but since they told us that g of 2 is -7, we could also write this as -7 plus the integral from 2 to 4 of f of t dt. So our answer is C. Finally, number 9. And how are we doing on time? We doing okay? I think we're going to be cutting it close, but I think we are making we're supposed to do this in under 18 minutes. I don't have a timer in front of me, but just keeping track of the time, I think we're going to be under that 18-minute mark. But hopefully, I'll check after the recording to see if we made it. So number 9 says the graph of f prime is shown below between -2 and 5. On what intervals is f increasing? So if f is increasing, that means f prime is positive. In other words, f prime needs to be above the x-axis, and we can see it's above the x-axis between -2 and 3, and that's it. So our answer is B. So that's about enough of the no calculator problems that we're going to be working on today. The rest of these are going to be calculator, and we're going to have 11 questions. And on the calculator section, you get about 3 minutes per question. Remember that there are a total of 15 questions on the actual AP exam, and you get 45 minutes to do that. So let's go ahead and get started. Number 10 says oil is leaking from a tanker at the rate of RFT equals 2,000 times E to the power of -0.2 T gallons per hour, where T is measured in hours. How much oil leaks out of the tanker from time T equals 0 to T equals 10? Here we just want to find the integral from 0 to 10 of that function R of T dt. So we're just going to type that into Desmos here. R of T is 2,000, and Desmos doesn't like the commas, so we're going to leave that out. E to the power of -0.2 T. And then we're going to find the integral of that function, 0 to 10 R of T dt. We don't really need the graph here because we're just doing a computation. We have our answer here. One other thing I want to throw out is that you don't have to write these as two separate entries. If you just put this expression here, you're going to get the right answer. Just make sure if you've got an expression there, you put it in parentheses just to be on the safe side in case you have a sum or something like that. So you don't have to do it separately. I just really like to define the functions separately so that I can refer back to them, especially when there's multiple parts to a problem. It's nice to have the functions defined so I don't have to retype the function every time. Here, you don't really get a whole lot of advantage there, but it's not a bad it's not bad to write these separately like this. So anyway, we can see that our answer is D. Number 11 says is if f prime of x equals sine of pi to the pi times e to the x divided by 2, and f of 0 equals 1, then what's f of 2? Here we're going to set up a fundamental theorem of calculus equation where the integral from 0 to 2, which are going to be these two x values here, of f prime x dx is going to equal the antiderivative of f prime, which is just f, evaluated at 2 minus f of 0. So if I'm trying to solve for f of 2, I'm going to isolate f of 2 in this equation. So I need to add f of 0 to both sides. So f of 2 will equal f of 0 plus that integral. Notice I'm not actually writing f prime here. There's no real reason to do that. We'll do that once we get into Desmos, but this is basically it. The only other thing that we'll have to make a note of here before we type it in is that f of 0 is 1. So when we type it in there, f of 0, that's just going to be 1. So let's go ahead and exit out of these two. We don't need those anymore. We're going to type 1 plus the integral from 0 to 2 of f prime x dx. Now here we haven't actually defined f of x yet, so let's go ahead and do that. Now we don't actually have anything, we don't have any reference for f of x, so I'm just going to call, maybe I'll call it g of x, that function that was given. So g of x here is just sort of taking the, playing the role of f prime. It's just that in Desmos you can't define the derivative of the functions explicitly here. So I'm just going to call this g of x and type it in as normal. Everything else should be pretty straightforward here. So there's our function, and we want 1 plus the integral of 0 to 2 of this function. If you're not comfortable with calling this g of x, again, just like with the last problem, you can just throw in this sign of pi times e to the x over 2 in here instead of calling it g of x. But either way, we get our answer here, which is about 1.157. We can see that that is answer choice. Oh, not D, almost circled D there, C. Number 12 says a particle moves along a straight line with a velocity given by this velocity function here. Probably going to need to type that into Desmos, which we'll do shortly. What is the acceleration of the particle? So keep in mind here that acceleration is defined as the derivative of velocity. So if we want the acceleration at time 3, we are just going to type into Desmos. Once we get that v of t function inputted, we're just going to type in v prime 3, and it can actually handle that. You can't define functions directly, derivatives directly, but if you define the function, then it can handle that notation with the little apostrophe there. So we're going to type in v of t, and that is 7 minus 1.01 to the power of negative t squared. And so what I want is the derivative of that, because remember, acceleration is the derivative of velocity at 3. And so, yeah, that's basically it. So this is going to equal 0.05. And on these multiple choice problems, the answer is always rounded versus truncated. I know for free response items, I try to tell you to truncate instead of round because it's one less decision to make. But with multiple choice, you're not really going to have a choice. It's going to always be rounded. So our answer here is B. Number 13 says a particle moves along the x-axis so that any time where t is positive or 0, its velocity is given by this function here. Again, we're probably going to have to type that into Desmos. We'll come back to that. What is the acceleration of the particle at t equals 4? This is basically the exact same problem that we had in number 12. The acceleration here, again, is just the derivative of velocity. So if we want the acceleration at time 4, we're going to want the derivative of velocity evaluated at 4. Same basic process here. This is really just the same question, just a different function here. So I'm going to type 3 plus 4.1 times the cosine of 0.9t as my v of t. And here I'm looking for the acceleration at time 4. So I'm going to type v prime 4, and that's going to give me 1.632. I guess that would round up to 1.633. So our answer is A. Number 14 says an object traveling in a straight line has position x at time t. If the initial position x0 is 2 and the velocity of the object v of t is this function that's given, what is the position of the object at t equals 3? So this is going to be a fundamental theorem of calculus equation, kind of like we had in number 11, where we want to set up the integral from 0 to 3 of v of t dt. And that's going to be equal to, now here's something that we didn't really talk about earlier, but we've talked about in the past, and that is velocity is the derivative of position. So velocity is the derivative of position. So that's one thing to make a note of. The other thing is when we go to type this in, we do have a cube root here, and there is a function in Desmos for you to type in cube root. But just because I think it's more convenient to write these cube roots, really any roots, as exponents, it may be worth noting that the cube root of 1 plus t squared is really the same thing as 1 plus t squared to the 1/3 power. It may be easier to type it in there. Again, if you search through the functions that are given on Desmos, I'm pretty sure you can do a cube root. In fact, let me take a look real quick and see if that is true. Functions, do we have a cube root here? Maybe not. Oh, yep, it's right here. So this will set up like a cube root for you, and you can type in 3. But I think if you understand that the cube root is just a 1/3 power, that's going to pay off later, in other problems for when you're using power rule and things like that when you're trying to differentiate or integrate. So it's good practice to rewrite any roots or any fractions as powers. So coming back to this problem, the integral of velocity is position, so with this fundamental theorem of calculus, the integral from 0 to 3 of vt is really just the position at 3 minus the position at 0. So if we're interested at the position at time 3, we're going to add x of 0 to both sides. So x of 3 is equal to x of 0, which, by the way, was 2. So, yeah, this is just going to be 2, plus the integral from 0 to 3 of vt dt. So all that we can throw into Desmos here. First, I'll type the velocity function v of t equals, and I'm going to use the power notation here, 1 plus t squared to the 1/3 power, rather than write cube root. Again, you can search through this functions button to find that cube root, but you're probably used to rewriting it like this anyway, so that's how I'm going to write it. So here we've got 2, which is that x of 0, plus the integral from 0 to 3 of vt dt, and that's going to give us approximately 6.51, and it'll round up to 2, giving us an answer choice of D. Number 15 says a pizza heated up to a temperature of 350 degrees Fahrenheit is taken out of an oven and placed in a 75-degree Fahrenheit room at time equals 0. The temperature of the pizza is changing at a rate of negative 110 e to the negative 0.4 t degrees Fahrenheit per minute. To the nearest degree, what is the temperature of the pizza at time t equals 5 minutes? Okay, so first, the temperature of the pizza is changing at this rate, right? And so one thing that I think maybe what we need to do is define a function for the temperature of the pizza. So what I'm going to say is let's just let f of t be the function that represents the temperature of the pizza. So that way f prime can be the rate at which the temperature is changing. So that would be the negative 110 times e to the negative 0.4 t. Okay, so here this is going to be just like the previous problem, another fundamental theorem of calculus set up here, where we have the integral from 0 to 5 because we have information about the temperature at t equals 0. We know the temperature is 350, but what we're trying to find is the temperature at t equals 5. So the integral from 0 to 5 of this f prime function, which is the negative 110 e to the negative 0.4t dt, should equal f of 5. In other words, the temperature at time 5 minus the temperature at time 0. So if we're interested in the temperature at time 5, we're going to add f of 0 to both sides. So f of 5, which is the temperature at time 5, is equal to the temperature at time 0, which is like your initial temperature, plus this accumulated change in temperature. Okay, now as I type this into Desmos, I'm not going to define, before, since I can't type in f prime in here explicitly, instead of calling it g, I'm just going to type it directly. Okay, so here I'm just going to type f of 0, which says in the problem the temperature at time 0 is 350. So 350 plus the integral from 0 to 5 of that change in temperature function, which I'll just type explicitly here, negative 110 e to the power of negative 0.4t. And then, of course, we need a dt in there. And so we get our answer here, which is approximately 112.217. It says round to the nearest degree here. So, yeah, our answer is for sure C. Now, before I showed you that you could name that derivative function. Which one was it? Oh, goodness, I don't even remember which one it was here. It was number 11. You could have named that f prime g, but you really don't have to. You can just type it in explicitly, just like we did in 15, and get the right answer either way. Number 16 says a particle moves along the x-axis for positive values of t, and is given, and the acceleration is given with this equation here. If the velocity of the particle is 2 at time equals 1, then the velocity of the particle at time equals 2 is what? Okay, so the acceleration, by the way, is the derivative of velocity, just like the derivative of position is velocity. So you have this sort of hierarchy where you have position, the derivative of position is velocity, and the derivative of velocity is acceleration, right? Not that we need to say anything about position here. I just wanted to briefly kind of go back over those relationships. So the acceleration is the derivative of velocity, which means we can use the fundamental theorem of calculus to solve this problem. So if we have the integral from 1 to 2, and again, the reason why we're picking 1 and 2, just like on all these other problems, is because those are the two times that we're interested in. We know the velocity at time equals 1, and we're interested in the velocity in time equals 2. So those are going to be what you want the upper and lower limits of the integral to be. So the integral from 1 to 2 of the acceleration is going to equal the antiderivative of acceleration. And remember, since acceleration is the derivative of velocity, that means that velocity is the antiderivative of acceleration. So using the fundamental theorem of calculus, we can say that the integral from 1 to 2 of acceleration is going to be equal to the velocity of 2 minus the velocity at 1. So if we're interested in the velocity at time equals 2, we can add v of 1 to both sides and get v of 2 equals v of 1 plus the integral from 1 to 2 of a t dt. And we're going to go and type that into Desmos. The only thing that we're going to change here before we type it in is that this v of 1 is 2. And it says if the velocity of the particle is 2 at time equals 1. So that's how we know that equals 1. So let's type that in. 2 plus, or actually let's type in, let me get ahead of myself here. The acceleration function is the natural log of 1 plus 2 to the t. And we want to find the value of 2 plus the integral from 1 to 2 of a of t dt. And there you go. Okay, so that's going to be approximately 3.346, which is C. Number 17 says that insects destroyed a crop at a rate of this expression that's given, that many tons per day, where T is measured in days. To the nearest ton, how many tons did the insect destroy during the time interval 7 to 14? So since we're just trying to find the accumulation of change here, how many tons did the insects destroy? All we need to do is just integrate this, this kind of crazy looking function from 7 to 14. So this is going to be exactly what we type into Desmos. We don't need to use fundamental theorem here. It'll do the computations for us. All we need to do is just make sure we type it incorrectly. So let's delete the ones from the last problem. And here we have the integral from 7 to 14 of 100 times e to the power of negative 0.1t over 2 minus e to the power of negative 3t. And if this is all you have typed in, you're going to get a little error message here. That's because you have to make sure you have that differential there, the dt. So this is approximately 124.994, but we are rounding to the nearest ton. So it's just going to be 125. And when you're rounding, typically the answer choices are not going to try to trick you. You're not going to get a problem like this where the answers are like 124 or 125 or anything like that. It's always going to be pretty obvious what your answer is if you do it correctly. Number 18 says, let f be a function with derivative defined by f prime equals sine of x cubed on the interval negative 1.8 to 1.8. How many points of inflection does the graph of f have on this interval? Okay, so points of inflection occur where the concavity of f changes. Let me write that down. Where the concavity of f changes. And this happens when f double prime, or the second derivative of f, changes sign. Okay, so what we're looking for is we're going to have to figure out how to graph the second derivative of this function and then count the number of times that it changes sign on that interval. So let's first by typing in that equation. Now, we've seen before how we can't type f prime explicitly here, so I'm just going to type g of x here, where we know that g of x is f prime. So g of x is sine of x cubed. And you're going to get kind of a wild looking graph here, but we're really just interested in the interval negative 1.8 to 1.8. So something like this. And if you really just want to see exactly what you're supposed to be looking at, you can do these little curly brackets and type in negative 1.8 is less than x is less than 1.8. Close the curly brackets, and that will give you the appropriate domain restriction. Let me bring that out a little bit so you can see. Okay, so we're looking at this graph, and this is, remember, this is f prime. This is not f. We just called it g because, watch this, if I try to do f prime, it's not going to let me do that. So I just have to give it a different name. And we're not even really interested in this particular graph. We're looking at, we want to count the number of times the concavity changes, although sometimes when you're looking at the graph here, it's not really obvious. Actually, this isn't even f, so we're not even interested in where the concavity changes here. We're looking at where the slope changes, right? So, so the slope of f prime changes once, twice, looks like 3 times, 4 times. Okay, so the slope's changing from being positive to negative right here, and then from negative to positive. So that's 1, 2. Doesn't change here. Still positive slope. It's all increasing in here, but then changes right here. That's going to be number 3, and then down here is number 4. But if you really want to see the graph of g double prime, it might be even more obvious here. So, f double prime. F double prime would be the same thing as g prime here. So if you just type in g prime, it's going to graph it. And we're only interested on this interval, so I'm going to put that domain restriction there too. I'm going to hide f prime. So now all I'm looking at is f double prime. We're looking for where f double prime changes sign, and that's going to be at all these x-intercepts where it changes sign. So we're not going to count 0, 0 because f double prime is not changing sign here. It's positive over here, still positive, so this does not count as a sign change. The only sign changes here are going to be right here. We got 1, 2. We're just counting. We're not actually trying to figure out where the points of inflection are, just how many there are. So there's 1, 2, 3, 4. Our answer is A. Number 19 says the function f has a first derivative given. What is the x-coordinate of the inflection point of the graph? We're going to approach this the exact same way here, except instead of just counting the number of inflection points, we're going to report back this x value wherever we find that. So let me change this g of x to be the equation that we're actually working with here. So we have the square root of x divided by 1 plus x cubed. And the domain restriction that we have on this particular problem is, actually we don't have any domain restrictions, so we don't even need that. And then we want g prime. Okay, so here, just remember that g prime is actually f double prime. And so what we want is to count, or we're not counting, we're just actually identifying where this changes sign. And we can see it's changing sign right here. It goes from being positive to negative. And so this happens at 0.47, I guess round up to 3. There's really no work to show here. My answer is C. Number 20 says the derivative of the function f is given by f prime equals x squared times cosine of x squared. How many points of inflection does the graph of f have on the open interval? Okay, we're kind of overdoing the points of inflection problems, but hopefully after this third one, you kind of get the point. So we're going to approach this exactly the same way we did before. We're going to call this f prime g. We're going to type in the equation x squared cosine of x squared. And this one we do have a domain restriction, so I'm going to throw that in there. You don't necessarily have to type in the domain restriction, but I find it helpful to really help you kind of zero in on what you're supposed to be looking at. And we have a lot of, this is going up and down kind of a bit, so I'm actually going to shrink this down. You can hold the shift key and click on one of the two axes if you only want to modify. Like here, I'm just doing a vertical dilation here so you can see it a little bit more clearly. So you can hold the shift key to do that. So yeah, we're looking right here at f double prime. Remember that g is f prime, so g prime would be f double prime. And it says how many points of inflection do we have? Point of inflection, just like we've been talking about before, occur anytime that f double prime changes sign. This is going to correspond to a change in concavity of f. And so we see that we're changing a sign here. That's 1. Here, that's 2. Here, that's 3, 4, and 5. So this is going to have a total of 5 changes in sign. So there are going to be 5 total points of inflection. And that's going to be about it. We really did pretty good on the time on here. We had 33 minutes, and we spent quite a bit less than that. I think part of that is just due to my familiarity with how to use Desmos. So during the test, if you take a little bit more time to type this stuff in, if you don't use Desmos as much as old Mr. Schuler, it's going to take you just a little bit of extra time here. So that's probably where that extra time is going to go. So as always, please reach out if you have any questions, and I'll be happy to help you. Otherwise, thanks for watching, and y'all have a great day.